Hello everyone, thank you for joining us and welcome to the live broadcast for the 10-year anniversary edition of MLatom. MLatom is a software platform enabling AI-enhanced computational chemistry in a user-friendly way, as MLatom is written by computational chemists for computational chemists. And we are very thrilled to announce the release of MLatom 3, marking its 10-year anniversary. This latest version comes packed with a wide range of exciting new features, including expanded simulations options, a Python API for tailoring workflows to your specific needs, and seamless integration with the XACS cloud computing platform, complete with an online terminal for easy access. So 10 years is a good point to reflect on MLatom's journey that started 10 years ago, started on September 10, 2013, and our core mission has always been clear from the very beginning: to deliver a versatile and user-friendly computational platform for atomistic machine learning simulations, catering for both beginners and experts. MLatom is recognized by independent researchers as one of the first packages catering to the needs of computational chemists, without extensive programming background, while also providing tools for easy implementation of custom machine learning algorithms. And over the past decade, MLatom has consistently evolved and improved. Here are some key milestones in the journey. As you can see, it rapidly grew after 2019, when its development base was formed at Xiamen University. And today, MLatom is a large package, and our anniversary edition is released under a very permissive MIT license. In this broadcast, we will overview the capabilities of this new release. MLatom enables many types of AI-enhanced computational chemistry simulations, such as geometry optimization, frequency and thermochemical calculations, molecular and quantum dynamics, and many different types of spectral simulations. Many of these simulations types have been added in this anniversary MLatom 3 release. But that's not all. MLatom goes beyond this, allowing you to train various machine learning models and their combinations with quantum mechanics methods and handle data. One of the most significant updates is the introduction of a Python API, empowering you to harness MLatom's capabilities with even greater flexibility and ease. There are basically two ways to use MLatom, including installing it on your local machine or cluster via pip install or git clone, or download it from the official website mlatom.com. And we recommend you using our online XACS cloud computing platform, where MLatom is already installed and set up for you. I will show you also later some demonstrations in real time how to use it. And this cloud computing is enabled by Xiamen Atomistic Computing Suite, which is available for free for academic and non-commercial uses. And for further information about XACS, see our previous broadcast. If you subscribe to our channel, you will see it. So here, overview of our social media and support channels where you can contact us and find information about MLatom and other XACS packages. So we provide real-time support via Slack community. You can also contact us via email. We have for Chinese users WeChat accounts, and also official website. You can find many extensive manuals and tutorials. You're also welcome to subscribe to this YouTube channel and to our accounts on Facebook and Twitter, X. So here we demonstrate how easy it is to use MLatom on an example of geometry optimization. The input file is very simple. It just tells the program which method to use, in this case the universal ML potential ANI1 CCX, and what task to perform. So in this case we want to do geometry optimization, and tells where to find XYZ coordinates with the initial geometry guess and where to save the optimized geometry. And here I will also show you some examples how to use it. on the browser. So if you go to XACS Cloud Computing Platform, you will see overview here. After you register and log in, you will have access to the terminal, file manager, job submit, and job manager. And if you want to submit some job like geometry optimization, you can find some input file, and which looks very similar to what we just discussed. So ANI1X here, you can choose to ANI1CCX if you want. I apologize for this. And then we have XYZ file with initial XYZ coordinates, and then we request to save it in this final.xyz file. So you can modify it if you want. For example, here we can switch to ANI1CCX. We save it, so we can close it, and now we can start this job by simply submitting it on the cloud. As you see, it's very easy. And after the calculations finish, you will see more files appearing, and now they are finished. So you see the geometry optimization are very fast with machine learning methods. And then here is optimized XYZ geometry, which you can look at, copy it somewhere in your favorite visualizer. And you can also check the geometry optimization output file, which tells you that after basically almost 30 iterations, it converged. You see the final energy, you see the standard deviation of neural networks, and you see this is of molecule 1, so basically you can run many molecules at the same time. So this is one way to do, which is, as you see, is very convenient. And now, if we go back to our presentation, so explanation about these AI enhanced computational methods, that now mature methods are basically compete with DFT approaches. And one of them is ANI1CCX, which I showed you, developed previously by some of our collaborators. And also there is AI QM1 method developed also in our group. And they are really much faster than DFT, and also very accurate, as you will see later. So MLatom supports not just ANI1CCX, but also host of other pre-trained ML models. And one of the highlights of MLatom is AI QM1, which I mentioned already, and it merges AI and QM approaches. And both methods are faster and more accurate than, for example, BIS-RELEAP approach. And here we demonstrate the power of AI-enhanced computational chemistry on an example of AI QM1. AI QM1 is a combination of neural networks and semi-empirical quantum mechanical methods that imparted with great speed. For example, geometry optimization of the full RNC60 takes only dozens of seconds. And although it is so much faster than typical DFT or ab initio methods, AI QM1 is also very accurate, so it doesn't compromise on accuracy, in contrast to many quantum mechanical approaches. And the AI QM1 approach is the gold standard coupled cluster accuracy for many properties of organic molecules, and one of such properties is optimization of geometries, which is done with excellent accuracy by AI QM1. As you can see here, correspondence to experimental geometries is truly excellent. And if you put it in perspective, it is typically much more accurate than popular DFT approaches, which sometimes fail even qualitatively for predicting the correct structures of challenging molecules. Here is an example of this C18 cyclocarbon. And you see that DFT predicts the wrong cumulonic structure, well, it should be with alternating triple single bonds. And it also enables fast predictions of hits of formation with chemical accuracy, which is a great achievement. for such a speed. And this high accuracy of AIKM1 helps to validate and even correct experimental measurements. For example, here for X-ray measurements, we corrected with AIKM1, also for hits of formation. And to emphasize, this method does not need any fine-tuning and is already applied to describe experimental observations of big nanolosses, including the prediction of geometries, binding energies with fullerenes, and the calculation of fluorescence properties. MLatom leverages the power of many other state-of-the-art packages for both quantum chemical and machine learning simulations by combining them into seamless workflows. So we heavily rely on different interfaces to give more flexibility to your workflows. And we just see how AIK1 is good at optimizing like ground state geometries, and that is also a result of these interfaces to semi-empirical quantum chemical packages like MNDO and Sparrow, and also Torch-ANI, which is a neural network engine. And we also have dependence on other interfaces for different applications. So these interfaces impart MLatom with the ability to perform simulations with the universal ML potentials, mostly for funny family, and some of them you already saw. We also have hybrid QM-ML approaches such as AI QM1, and even we can perform pure QM simulations with DFT, ab initio, and semi-empirical methods through various interfaces. The user can easily choose a method and interface via simple input files. And many of these methods are available on the XACS cloud computing to make AI-enhanced computational chemistry easily accessible to everyone. And for more advanced users and developers, our new anniversary edition of MLatom provides a possibility to use all its functionality via flexible Python API. And you can use this API to construct your own flexible workflows. So this is for more hands-on approach, and if you go to this XACS Cloud Computing website and click on Computing, so you will see this page, and instead of submitting jobs, instead of writing text files, you can actually go to terminal and run it as a Python script. So let's look at the same example we just shown before for geometry optimizations. So we can do it differently. We can actually now you do it in Python. So we can import MLatom, SML for example, and then we can do several things. So first we can define our method which we want to use. So that will be ML models methods and method equal ani1 XACS. So this will create our method which we want to use. You can customize it with another machine learning potential, even trained by yourself. And then we need some kind of initial guess of a molecule. So let's say init molecule equal ML data molecule. And then we need somehow to read at least the initial coordinates, or you can define it yourself. Read from. So actually you can look up, we have many different properties, right? And for molecules you can access many different functions also. So you can read this from XYZ file, you can read from smiles, and you can also get many different properties of a molecule. And let us read from XYZ file, and file name would be init XYZ, right? So sorry. Okay, and now you see we created a molecule object, and finally we can optimize it. So to optimize it, we would need to define our procedure. So we need to request simulation. And we need to request optimize geometries. See, there is a nice autofill for you, so you can just do this very easily. And then we choose our model. So our model is Ani, which we just created above, right? And since we have already our Ani model, we also need to say initial molecule. So that should be initial molecule equal init-mol, right? And that's basically it. So it's already does optimization for you. So similar output as you saw before. After almost 30 iterations, optimization converged. Now you can get our optimized molecule from this object. See, you get this optimized molecule. And for example, you can look at the energy of it. Or you can even, so we are interested in geometries because that's what we got, and geometries should be, you can see them, if you are just interested in coordinates, you can get XYZ coordinates, so there is a special function for it. You can also get some string, so it's basically up to you. You can save it on the disk because that can be useful later, right? So what you want to do is, for example, write XYZ file with XYZ coordinates, and then file name can be opt XYZ like this, and that is done. So now we can exit this, and you see we've just created this opt XYZ file, and you can check it, so it's there. And again, the very nice thing is that if you go to file manager, you can later find it, so you can modify it, submit somewhere else. So this is your optimized geometry now done in Python API. Basically, we just released yesterday night this new Python API, so you are the first to see how it works. And you can do many more with this, so this is just a small example. Again, I will just show you that here MLatom provides you also on the website different supports. So here is manual for MLatom. There is also some workshop materials, tutorials, and manuals can be quite comprehensive, so they talk about running an installation, the package. They also give overview of different possible simulation scenarios. Like for example, we were discussing geometry optimization, so here are more options which you can choose for you and explanations for them. We will also have soon online documentation of MLatom PyAPI, which we are now preparing for release. So you'll find more of this information on the web resources. And I was mentioning that of course you can build your own machine learning models, and you can also choose from many popular machine learning models which already were developed in the literature. And for example, we have a nice choice of different types of machine learning potentials, both based on neural networks and kernel methods, and also which support local and global and learn descriptors. And the users can easily train these and custom machine learning models, optimize their hyperparameters, and evaluate their performance with all our options. And it is very easy to switch from one model to another. So input file estimating accuracy of kernel method model, CRAC, would look very similar to the input file for the ANI model. So you can train your own neural network ANI type model on your data. And after you train it, you can use it for many things, like calculating geometries, optimizing geometries, running molecular dynamics. And dynamics has been also made available in this anniversary edition, and many different types of dynamics are supported. So in this example, we show a typical input file for the molecular dynamics in the NVT ensemble, and which uses also the CRAC model. And then it will output you different trajectory files. And after you generated these trajectories, you can actually generate vibrational spectrum from it. And the input file is also quite simple, so you just need trajectory and then some other options, many of which you can just use default ones. And then if you use one of our pre-trained models, such as AIQM1, the spectral quality is of high quality and usually better than with some empirical or even DFT approaches. So this feature is also new in MLatom 3 Anniversary Edition. We also have many unique AI-enhanced dynamics approaches. And here, for example, we predict quantum dynamics directly as a function of time using AIQD approach through the interface to the MLQD program. We also have methods for molecular dynamics, which similarly predict positions of nuclei as a function of time, and they will be released separately. And as I mentioned before, machine learning can be used also to generate vibrational spectra, but also different other spectra, right? So in addition, we can also use machine learning to generate AI-enhanced simulation of UEV's absorption spectra, which is much faster than using traditional quantum mechanical approaches and also more precise. Another feature, and here also defined solvent. And finally, your output will give the predicted two-photon absorption cross-section for different wavelengths for which you decided to run the calculations. Well, basically, that's it. So thank you for joining our live broadcast and welcome to subscribe to our channels. If you have any questions about MLatom, here is again, we have many different channels where you can contact us. So you can contact us through email, you can contact us through Slack, which is advisable to do because then we can really efficiently reply in real time. We can connect to developers who know better how to answer your questions. And we also have WeChat, which is very convenient tool, and to get more news and updates about our releases and packages, you can check and subscribe to our groups on Facebook and Twitter. So I will check whether there are any questions. So if there are any questions, I can still wait a bit, but basically I thank you very much for your attention. So I will update the description link later after this broadcast is finished with all these links to supporting, and also you will be able to watch this and in replay and share this video with others. So thank you very much. I will now stop the broadcast.